Welcome, ladies and gentlemen. Good morning. May I have your attention, please? Thank you. Raise your hand if you didn't get a red mark for today, the 13th. All right, so being able to apply the chain rule, right, it's our most important rule thus far in our derivative unit 3. It combines, right, multiple rules into a single composite function. So now we wouldn't have to expand this 2p minus 3 all to 100 the way that we would have to, right, prior to the chain rule, because there's clearly an overall outer function and an inner function, right, an inner function in this situation. And so as I look at number 1, would you say the overall function is a linear function or a power function, right? Is the overall function the linear function or the higher power function of higher degree? Savannah?
Power.
Power, I would agree. And so we're going to go ahead and consider this the derivative of a composition of functions is the derivative of the overall function. So that would be the power function. That would be exponent times the base raised to 1 less. So there's my derivative of the overall function using the power rule. My inner function then, evaluated at the inner function, would be the 2p minus 3, because it wasn't just x for my base in the power. It was 2p minus 3. Then, times the derivative of the inner function. So the derivative of my inner function, 2p minus 3, is simply 2. So I've got overall rule, derivative of the overall function, evaluated at the inner function, then times the derivative of the inner function, put it all together, and we'll get 200 quantity 2p minus 3 to the 99. Raise your hand if you already had that for number 1. So who had that for number 1? Excellent. So we're off to a great start with the chain rule. Let's go ahead and take a look at number 2. I'm going to be asking you what the overall function is versus the inner function. And so is the overall function in number 2 a trig function or a cubing function? So is it a trig function or a cubing function for the overall function? Jake?
Trig.
Trig, I would agree. And so when I do my words for the chain rule, I'm going to do the derivative of the overall function would be cosine goes to opposite of sine, right? Evaluated at the inner function, and then times the derivative of the inner function. So we'll go ahead and I'll use the same color coding. The derivative of cosine is opposite of sine, evaluated at the inner function. My inner function was the cubic, t cubed plus 2t, and then times the derivative of my inner function. The derivative of my inner function is simply 3t squared plus 2. Don't forget your quantity, and we could go ahead and rewrite it if we want to make it a little bit better. There's not a lot of fixing here. We could do negative, and we could leave this quantity if we wanted. 3t squared plus 2 times sine of... Probably won't break. Awesome. Raise your hand if you had number 2 correct. So did you get the trig overall? The trig overall? Way to go, you guys. And, you know, you could group that, you could rewrite that different ways, but that's fine for us right now. Let's go ahead and take a look at number 3. So the derivative with respect to k, I believe that it's easiest to rewrite this, right, first before doing my differentiation. And so overall, is this a radical function, or is it a polynomial function? So overall, is this a radical function or a polynomial function? Michaela?
Radical.
I would agree. Radical would be my overall function, my outer function. So when I go to differentiate this, I want to be able to rewrite that radical function, right, in power format so that I can utilize my power rule. So before differentiating, I would keep my derivative with respect to k. I'm not differentiating here. I'm just going to rewrite that radical function with exponents, my exponent rule. So this would be 11k minus 4k to the 5th. And a radical, a square root, is synonymous with what exponent, right? With what exponent? Brandon?
1/2.
Absolutely. So thank you. By writing this as a power function, I can now use my power rule. So the derivative of a composition of functions is the derivative of the overall function. This is a power rule. Exponent times the base raised to 1 less. What's 1 less than 1/2? Negative 1/2. So there's my derivative of the overall function. Evaluated at my inner function. What's my inner function? Well, that was the polynomial 11k minus 4k to the 5th. And then times the derivative of the inner function. My squiggle underlined inner function would have derivative with respect to k, 11 minus 20k to the fourth. There's my derivative of the inner function. Everybody see it? A quick regroup, and I can rewrite this as positive exponents and change the fractional exponent back into a radical. I know a negative exponent doesn't mean negative answer, it means reciprocal. So this would be 1 over quantity to the positive 1/2, and we know from the beginning that a 1/2 exponent is synonymous with a square root. So let's put it all together. My final answer would be 11 minus 20k to the fourth all over. That 2 would jump down, radical for the 1/2 exponent on the bottom, and 11k minus 4k to the fifth inside. Did I get everything? Yeah, we got the positive exponent on the bottom, would be positive 1/2, change it back to a radical. This quantity stays on top, but the 1/2, the 2 would kick down to the bottom, the 1 would stay on top, and I'm getting this as my rewrite. Okay, I'm dying. Did anybody get this? Raise your hand if you got this. Couple? A sprinkling? A smattering? Yes? What questions do you guys have on number 3? That's pretty sweet. So if we start out with the radical, right, we probably want to change it back into radical form. In general, just for good math manners. And we probably don't want to leave answers with negative exponents necessarily unless we were given with negative exponents. So that's okay. Awesome. All right. So now I'm not going to ask whether the overall function is a trig function or the inner function is a trig function, because yes and yes. What I am going to ask is the overall function a sine or a cosine. Is the inner function a sine or a cosine? So for overall function here, when I do my composition, is the overall function a sine or a cosine? Hayden? Sine. Good. So when I do my derivative, all right, of this composition of functions, I'm going to start with the derivative of a sine function. I know that sine differentiates cosine, evaluated at my inner function. So this would become cosine of evaluating my inner function. What was my inner function? Well, my inner function is cosine of theta. So this is first step. The derivative of my overall function sine goes to cosine, evaluated at the inner function, and then times the derivative of the inner function. So what's the derivative of my inner function? Well, that would be the derivative of cosine theta. What does cosine of theta differentiate to? Opposite sine of theta. So I've got cosine of theta times negative sine of theta. And if that's not a tongue twister, stay tuned because we've got a number 5 lurking around the corner. Don't be shy. We've got negative, I probably grouped that, sine of theta in front of the cosine of theta. Could I rewrite this as negative sine theta cosine squared theta? Right? Could I rewrite this as negative sine theta cosine squared theta? No, this is cosine of cosine theta. This is an operator here. It's not a factor. Cosine theta times cosine theta is cosine squared theta, and we see that there's only a single cosine theta as my angle input in this overall cosine function. Wow, that's great stuff. So I'm dying to know who got number 4. Did anybody get number 4 right? You did with the overall. Hey, that's great news because that's going to be a good setup for number 5. Dun 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 dun. So I tried to include a stretcher, right? Some of you are rock styling like number 1. You're doing very well on. Number 4, very well on. What's going on in number 5? Well, yikes. Number 5's got a whole slew, right? A whole slew of functions. We've got squaring, we've got trigonometric functions, we've got inner functions, we've got power functions. How are we going to figure out how the chain rule will help us differentiate this expression? Well, I think we have to go back to our original equation for a composition. What's the overall function here, right? What's the overall function here? Is the overall function here a sine function? Is it a power function? Is it a cosine function? Is it a quadratic function? Oh, goodness. I think that it might be helpful just to rewrite this. I'm not differentiating yet. I'm going to keep my derivative with respect to theta, and I'm just going to rewrite this. I'm just going to rewrite this as a squaring function. Recall my shorthand notation, that sine squared means sine of an angle, right, times itself, sine of an angle. And my angle in this case was cosine of theta squared. Let's take a minute and make sure we understand that rewrite. So we took our original sine squared of cosine theta squared and we rewrote it as a power function explicitly. So we can see that we've got sine of cosine theta squared is all squared. Does everybody see that? Now it's plain to see my overall function is a squaring function. Right? This is a squaring function now. The derivative of a squaring function is the power rule. Exponent times the base raised to 1 less. So let's go ahead and start out with my overall function now. Exponent 2 times the base raised to 1 less. There's my power, right? There's my power rule. What was my inner function? My inner function was sine of cosine theta squared. Right? So there's my derivative of the overall function. Now I still need times the derivative of the inner function. Well, my inner function is a double duty. Well, I should say a triple duty. It's that sine function in green, which includes an angle input that itself is a composite function. That is to say, my current inner function is sine. What does sine differentiate to? Well, sine differentiates to cosine, right? So the derivative of sine of theta is cosine of angle input. It just so happens that my angle input is itself composite. My angle input is cosine of theta squared. So I now need times the derivative of my inner function. What does cosine of theta squared differentiate to? Well, is this overall a squaring function or a trig function in red? Is that overall squaring or overall trig? This is the overall trig. To be squaring, it would have to be cosine squared theta, not cosine theta squared. So this is overall trig rule. No problem. The derivative of cosine is opposite of sine. Evaluate on my inner function, then times the derivative of my inner function. What's my inner function? Theta squared times the derivative of my inner function. What's the derivative of theta squared? We're almost there. 2 theta. So did I make enough? Almost? Don't be shy. Oh boy. Oh boy.
I don't understand.
Look at that.
I know.
Stay strong. It's all right. So here we go. The derivative of squaring is exponent times the base raised to 1 less times the derivative of the inner function. Sine differentiates to cosine with the angle, right, with the input, times the derivative of the inner function. Cosine differentiates to opposite of sine with the input. Then, times the derivative of the inner function is finally down to the derivative of theta squared with respect to theta, which is 2 theta. Wow! So we'll put it all together and see if we can regroup this at all. I get a negative, I get a 2, I get a 2, and a theta, so I'm thinking my linear term here is just going to be negative 4 theta. And it looks like we've got a sine of theta squared. And it looks like we've got a sine of cosine theta squared times the cosine of cosine theta squared. Now, if you didn't get number 5 at this juncture in your lives, that's okay. I wanted to include a stretcher so you could see, right, the complexity of the chains that can be built utilizing the chain rule and composition of functions, and see where we're headed, right? And so on our very first day, everyone should have been able to accomplish our differentiation, right, with number one. And as we went through these first couple, right, we had to do a rewrite for some. Number 2, no problem, all that's fair game. Number 4, you guys did very well with. Number 3 included exponent rules, so there's a little stutter step. And number 5 is meant to be a stretcher, right? I want to challenge you guys. I want to push you beyond and a little bit further along. We're going to get some practice today. I made an extra chain rule practice handout that will be included as part of our OTL number 9 for you to practice with just this, the chain rule, so that you can work towards being successful with problems that look like number 5. Anna?
When do you know to use the chain rule?
Great question. So when do we know to use the chain rule, right? When do we know to use the chain rule? If my original function, right, is a composition of other shortcut rules that I know, then it's a candidate for use with the chain rule. So if I can express the original as a composition of functions, then the chain rule would be appropriate to use for differentiation. Do you see how that could be a composition of functions with an overall and an inner? Good. An overall and an inner? Absolutely. Great question. Other questions on today's Bellwork? Okay. And let's go ahead and take care of our OTL number 8, which includes derivative interpretations. The derivative interpretations had some multiple answers and responses are fine. Some of those we're interpreting at the end, like those last letters, D and E, were kind of up to you. Based on your real world experience or what you've seen in science, you could certainly justify different responses. I include on the answer key what I would have put, right, in those different situations, but there was some guessing and interpreting as you got towards the end. However, the first several interpretations had to match, right, because they included the units given in the original function example. Such will be the case with your Moodle post this week. And so recall, our derivative interpretations from the soccer jersey example becomes a conversation starter for our Moodle post this week. Some of you have already posted for the Moodle post, and thank you for that. Make sure you check out the discussion forum. I put the directions for the prompt early Monday morning, and you must you must post your original function example in accordance with those directions by Thursday, 11:59 p.m. Moodle time in order to receive the first 3 points. This week is a reply to a classmate week, so you're going to read responses posts of original function examples, and then choose a classmate to reply to in accordance with the directions in the prompt. You will reply to a classmate and use their given point and derivative value to make a prediction, right? To make a prediction of a subsequent function value. Don't forget to include units in your interpretation. And again, to receive another 2 points, that's by Sunday, 11:59 p.m. Moodle time. And there's some great function examples up there already, so I look forward to reading the rest of yours. Awesome. Go ahead and give yourself credit for those you complete out 19. This includes the derivative interpretations. We'll go ahead and staple. We'll go ahead and staple multiple pages together. You can put whichever on top, so long as you got your Infinite Campus score through the box runs and there's half point in your name.
Does derivative interpretation packet staple?
Yeah, please. So that includes the derivative interpretations packet, please.
No, I think it's just the.
Okay.
And after you've stapled, go ahead and pass them back to the front, please. Someone, if you kindly make sure they're facing the same direction, I appreciate that. Okay. Everybody good with number 8 if you did it? Number 8? Okay, ladies and gentlemen, I'm super excited about today because today we're going to add our final shortcut rules from Unit 3, derivatives. Okay, so we've got our chain rule from last time. I put that on the top right side of our derivative rules whiteboard. Make sure you have that added to your derivative rules sheet in your binder. What we're going to do today is investigate exponential functions and the natural log function and determine shortcut rules for those. Whether I have a natural base e exponential or a non-base e exponential, we're going to determine a rule by the end of today's classroom, and so that's exciting. What I want you to do right now is don't go into your groups, but just with your partner, I want you to go ahead and sketch in a derivative function in pencil, a positive derivative function in pencil for the two functions shown on your warm-up. So everybody find your warm-up. That's a single page. I want you to talk with your partner about how you could represent the steepness of the original and slope of it anywhere along it without a scale on the y-axis, to just generally sketch a qualitative picture of the graph of its derivative. So you can go ahead and talk with your partner about this and see about answering the questions it would ask, like the function family and so on and so forth. So just do this with your partner. Don't split the desks. Think about how that would look using your knowledge of derivative sketches. derivative graph represents the steepness of the original function. Now you can show that qualitatively for your sketch.
No.
You're right.
Awesome. Okay, ladies and gentlemen, let's come together and see how our sketches compared with your classmates. And so let's take a look at the first one. In the first one, my function family from the first one, what type of family did the first original function appear to belong to? Michaela? Yeah, exponential for the original. So the first one appeared to be an exponential function family. We see as you move to the right along this function's domain, that function begins to increase at an increasing rate. And we've got a horizontal asymptote at y equals 0. That must be an exponential function family. Compare that with the family of the derivative. What function family must the derivative belong to given Hayden's sketch? So what family does the derivative appear to belong to? To S? I was just wondering, how did the derivative graph appear to relate to the original graph? What function family is that? Absolutely. And so it appears that the derivative graph is also exponential. Thank you. Right? So raise your hand if you had exponential for both original and derivative family. Perfect. Let's go ahead and take a look at Jake's sketch. And so my phone, yes?
For that one, does the derivative graph have to be below the original graph?
That's a great question. Our y-axis for the derivative graph is purposely left unscaled. And so we don't know, right? We don't know what values are on this y-axis that represent the original function values or the values of y prime, the first derivative. And so it would be perfectly acceptable, right, to have our derivative graph higher than the original graph, right, depending upon the steepness of our original curve. We're going to have some constant there is going to determine that original y-intercept, and we're going to figure out today what that constant is. The key, however, is that the graph is increasing at a rate proportional to the value of the function itself. If I'm further along on my graph, if my y-coordinate of my original is higher, then the steepness of the curve must also be greater. If a y value of the original is lesser, then the steepness of the curve must be lower. Does everybody see that? So the higher I get up on the y-axis of my original graph, then the steeper the function is, that corresponds to greater values on the y-axis for my derivative graph. Does everybody see that? Awesome. Jake, thanks for doing this sketch. Take a look at my original slope values as I'm close to x equals 0. But to the right, my slope values for the original are very large. How can we show that in the derivative graph? Well, let's get very tall y values, right, on my derivative graph for the same input x. Look at how high we are here. And as we move further to the right in this original function's domain, notice how my rate of increase lessens. Still positive, but lessens. How can we show that in our derivative graph? Well, we're going to remain positive, but closer and closer to the x-axis. The magnitude of the slope values of my original lessen as we move along from left to right. Therefore, I must show the magnitude but my derivative y coordinates are lessening as well. All right? Does everybody see that? Raise your hand if you had a similar sketch to Jake. Good. So what is my original function family? What does my original function family appear to belong to? Well, this key point at x equals 1, comma 0 is shown on purpose, right? Raise your hand if you're willing to guess the function family of my original. What do you think my original one is? Hayden?
Square root.
This is my original square root. That's a great guess. Let's see, if I was a square root, then my x coordinate 0 would be paired with what output?
Well, it's not positive.
Yeah, so we'd have to have 0, comma 0 if this were the square root graph. So it's not square root, right? No problem. What other function family could this belong? Paul?
A log.
Yeah, this is a logarithmic function. So my function family is a logarithmic for the original. Good. The logarithmic function family for the original. And what does that derivative function family appear to be? What does that derivative function appear to be? For this, we've got to go way back. What does it look like? Evie?
Is it exponential decay?
Ooh, that's a good idea. Except that my domain for exponential, even if it's growth or decay, would be all reals, and I would have to have a y-intercept and continue to the left. So it would look exactly like this, but flipped left, right. So it can't be exponential decay because I'd have to have all real inputs x, and my graph would extend farther to the left. But the shape matches that, doesn't it? Kind of. Hayden?
It's like a half hyperbola.
It is kind of like a half hyperbola. A half hyperbola, right? This is, in fact, is a branch, right? A branch of a hyperbolic function. Depending upon what my base on this logarithm is, it actually comes from hyperbola. Let's see. What would the equation look like for a hyperbola? What would the equation look? I know the graph looks like my branches, right? What would the equation look like? Brandon?
Well, I don't remember for sure, but I believe it was something like x squared minus y squared.
Oh, for the general form of a conic for a hyperbola. Yes, that's correct. What I'm talking about is our basic function family, right? That has y solved for, and that was 1 over x. Or inverse power. So we could say inverse power. And remember, inverse power could look like k over x to the n, right? For a hyperbola, in general, it could just be 1 over x. If we're looking at our basic parent function for the hyperbola, 1 over x. And then we need to transform it back. Awesome work, you guys. Okay, today we're going to nail down these shortcut rules. Right, exactly. We're going to generate our final shortcut rules of Unit 3. I'm super excited about that, and we're going to add them to the back whiteboard for shortcut rules and our derivative shortcut sheet. So, everybody, exponential and logarithmic functions activity. In your activity, we'll get stamps at 4B, 5B, 7, 9. In order to get your 9 stamp, you'll need to rewrite exactly without decimals. And so we'll be looking for a particular constant that can be written exactly without the use of decimals in order to get your 9 stamp. And then like yesterday, like last class with the chain rule, at the end of your practice, you'll be able to get a stamp. Make sure you're checking with the answer keys though, and it's okay to use your smartphone when you get to the practice to access our Moodle website so that you can check your answers. That's totally appropriate when we get there to your practice. And many of you, right, will need to complete that practice as part of your assignment in order to get your stamp during Bellwork next time. Okay, so to that end, let's go ahead and get started. I want you to scoot together into your groups. I'll pause the recording, and I'll leave the stamped eligible items up on the sideboard as well. Thank you, ladies and gentlemen, for your help returning their desks to the regular position. Everybody, I want to go ahead and point out one thing from your practice that will help make your life easier when you get to number 5. I saw Jake was already utilizing some properties of logarithms that make this differentiation much easier. And so instead of doing an overall function and an inner function for chain rule, Jake recognized from his logarithmic properties that he could rewrite his original y, not differentiate, just rewrite the original y by bringing that exponent down and rewriting it as 3 times ln x. Then when he differentiates y to get dy dx, the first derivative, he no longer has to use the chain rule. He can just do the constant multiple rule. Constant times the function is the constant times the derivative of the function. And so by rewriting this using logarithmic properties with exponents, he was able to create an easier first derivative, which resulted in an easier second derivative. Okay, now let's go ahead and complete our closure. So for our closure, we develop our last 3 shortcut rules for the unit. So the derivative with respect to x of e to the x is, don't say it out loud, write it down. The derivative with respect to x of ln x, be ready to share it, so I'm going to call on you. The derivative with respect to x of 4 to the x, and a general constant a for exponential base a. The derivative with respect to x of a to the x for constant base a. Awesome. Let's go ahead and share your response with the whole class when I call on you. So our last 3 shortcut rules for Unit 3, the derivative with respect to x of natural base e exponential, e to the x, is what? Jake?
E to the x.
E to the x, the exponential itself. Wonderful. The derivative with respect to x of ln of x is what? Right? What is the derivative of ln of x? Allie? 1 over x. Good job. What's the derivative with respect to x then of non-base e exponential, like 4 to the x? What would that look like? Anna?
Natural log of 4 times 4x.
Absolutely. It's the exponential itself still, but then times this constant times the natural log of the base that you guys discovered in your activity. So how could I generalize that for constant base a to the x? The derivative of a to the x with respect to x then would be what? Monica? Awesome, ladies and gentlemen. Let's go ahead and add those to our rule sheet. So we've got our final shortcut rules, and I'm going to leave it like that for B-Day, right? So you guys can fill it in using your closure. And we'll be good to go. I'll stop the recording here, and I'll say nice work. You can still get your practice stamp tomorrow or next class during Bellwork.